Tuned amplifiers are amplifiers which employ tuned circuits, parallel LC resonant circuits as load. They are used mainly to amplify high frequency signals like radio frequency signals. They are employed mainly as front-end selective circuits in the design of radio receivers. When they are used as front-end selective circuits, they need to perform two things. One is providing a huge amount of gain. Single stage may not be able to give large amount of gain, sufficient amount of gain. For this reason, people go for multi-stage configuration when it comes to tuned amplifiers used in the radio receivers. Second aspect to be fulfilled by the tuned amplifiers is selecting or picking up the wanted or desired signal and at the same time discarding, rejecting unwanted signals. Only wanted signal is allowed into the receiver, amplified, and then it is given to the remaining part of the receiver circuit for further processing. Tuned amplifiers may be narrowband amplifiers, they may be wideband amplifiers. They may have sharp selectivity, they may not have that much sharp selectivity. All that depends upon the tuned circuit, the characteristics of the tuned circuit, especially on the quality factor of the tuned circuit. It is the tuned circuit that matters most as far as the performance and design of a tuned amplifier is concerned. Multi-stage amplifiers, tuned amplifiers, part 1, series on semiconductor devices and circuits, lecture number 8.14. Tuned amplifiers are high frequency amplifiers, radio frequency amplifiers. They are front-end amplifiers of radio receiver circuits. These amplifiers get their input from the receiver antenna. The signal then is amplified by the tuned amplifier chain before passing it to the remaining part of the receiver circuit. In this session, the focus is on features, characteristics, types of tuned amplifiers. We now proceed to begin the session on tuned amplifiers. We begin the session by mentioning certain general points pertaining to tuned amplifiers. Tuned amplifiers are high frequency active circuits widely used as front-end portions of radio receivers. A radio receiver usually consists of an antenna, receiving antenna. The receiving antenna collects the signal from space, and it gives this signal to receiver circuit through a multi-stage amplifier. This multi-stage amplifier is a chain of tuned amplifiers. So the receiver circuit starting point is tuned amplifier chain or multi-stage tuned amplifiers. Their load is a tuned circuit, usually a parallel LC circuit. The load of tuned amplifiers is a tuned circuit, a parallel LC circuit. To understand their functioning, we have to consider two facts. We must keep these two aspects in our mind while studying tuned amplifiers. The gain of the amplifier is, in general, directly proportional to the load impedance. Voltage gain. It is proportional to load impedance. More the load impedance, more is the gain, less the impedance, less is the gain. The impedance of parallel LC circuit is maximum at its tuned frequency and falling to low values at frequencies away from the tuned one. So this is the property of parallel LC circuit. This is the property of amplifier circuit. When amplifier is carrying a tuned LC circuit as load, then what happens is its gain is large when it is working at a tuned frequency of the LC circuit, and gain falls as the frequency falls away from the tuned frequency. Here is shown single stage tuned amplifiers. Two types are there: capacitive coupled, inductive coupled. Tuned amplifiers, they can be single stage amplifiers, they can be multi-stage amplifiers. Here right now in this slide you are seeing single stage amplifiers. Single stage because only one active element is there in circuits shown in A and B. Notice LC, parallel LC circuit is there as load, parallel LC. So these two are single stage tuned amplifiers. Okay. A is capacitive coupled. Why it is capacitive coupled? Output of the amplifier is coupled to load through a capacitor C2. Capacitor is used, that's why it is capacitive coupled amplifier. R1, R2, etc. These are all bias resistors common to any amplifier circuit. RE is emitter resistor, CE is bypass capacitor. Okay, but important point here is A is capacitive coupled. Reason is the capacitor C2 is used to couple the output of the amplifier to the load. B is inductively coupled. Why it is inductively coupled? An inductor is used or a transformer is used to couple the output of the amplifier to the next stage or to the load. That's why it is inductive coupled. Of course, in both amplifiers, signal source is coupled to the amplifier through a capacitor C1. Here also C1. This is capacitive coupling. Coupling between source and amplifier is capacitive coupling. In A, coupling between amplifier and the next stage or load is through capacitor. In B, it is inductor. That's why amplifier shown in A is said to be capacitive coupled and amplifier in B is said to be inductive coupled. Here are shown gain characteristic of single stage tuned amplifiers. As already mentioned, gain is proportional to impedance of the load, and load is LC circuit, parallel LC circuit. Parallel LC circuit's impedance varies. it falls from its resonant frequency. At resonant frequency, it assumes maximum value. Impedance falls as you move away from the resonant frequency. In the same way, gain also falls. Tuned frequency gain also falls as you move from resonant frequency. In A is shown gain characteristic of tuned amplifier when it is capacitive coupled. In B is shown gain characteristic when it is inductively coupled. In case of inductive coupling, we can see in B there are two curves. One curve is similar to the curve we had in case of capacitive coupling, a bell curve. Another curve is also there. It is like sinusoidal curve or two bell curves side by side. One bell, another bell. One curve is for the case of loose coupling, another curve is for the case of tight coupling. Notice tight coupling gives least amount of gain, where loose coupling gives maximum gain. This is one aspect. Another aspect is loose coupling gives maximum gain at one frequency, whereas tight coupling gives maximum gain at two frequencies. Here we get maximum gain, here also we get maximum gain. There are 2 points where maximum gain is possible with the tight coupling. Another aspect is maximum gain available with the loose coupling is large when compared to maximum gain that is possible with the tight coupling. These aspects require to be there in our minds if we want to understand the functioning of tuned amplifiers in a deeper manner. Here is shown gain characteristics of a single stage tuned amplifiers A, B. In A is shown narrow band amplifier characteristic. See, this is bell curve is gain characteristic. Maximum gain point is associated with central frequency or resonant frequency. At frequencies F1 and F2, gain falls to 3 dB by 3 dB. The distance between 3 dB points is called bandwidth, 3 dB bandwidth. So F2 minus F1 is 3 dB bandwidth. This is the case of narrow band. F2 minus F1 usually is small. That's why this characteristic represents a narrow band amplifier. Come to B. Here is another characteristic. You can see gain is at high. Of course, some variation is there, but it is occupying high value over the wider frequency range. You can consider this as F1, you can consider this as F2. Notice F1 is called lower cutoff frequency, F2 is called upper cutoff frequency, FL, FU. F2 minus F1 is, or FU minus FL is bandwidth. In B is shown a characteristic for which F2 minus F1 or Fu minus FL is large. So the gain which actually represents the amplifier, that amplifier is called broadband amplifier. Selectivity is an important characteristic parameter pertaining to tuned amplifiers. So what is selectivity? As already mentioned, the basic use, fundamental use of tuned amplifiers is as the front end portions of a radio receiver circuit. Tuned amplifiers require to serve two purposes when they are used as front end circuits. of a receiver. One is to provide huge amount of gain. The received signal strength is usually very small. It has to be raised to a level where it can be used for further processing to extract the signal. So rising signal level is one aspect, one requirement as far as tuned amplifiers are concerned. Another aspect is pertaining to filtering characteristic. What is this filtering? At the receiver antenna, in addition to the desired signal, wanted signal, there exists several signals which are undesired, which are unwanted. Desired one is one among them. So this particular amplifier, tuned amplifier or tuned amplifier chain has to discard or avoid or prevent unwanted, undesired signals entering into the receiver, and at the same time pick up the desired and wanted signal. In other words, it has to choose, it has to pick up only the wanted, and it has to prevent unwanted signal entering into the circuit. Selectivity is a parameter useful to describe the capability of a tuned amplifier in picking up the desired signal while avoiding, eliminating, discarding the unwanted signal. Now a few points regarding selectivity. Selectivity is an important parameter, highly useful in the design of analysis of tuned amplifiers. It describes capability of a circuit in discriminating signals based on their frequency content. Tuned amplifiers require filtering out unwanted signals as well as selecting only wanted signals for amplification. They get this capability by employing tuned circuits which have the characteristic of selectivity, that is, allowing amplification only for the desired frequency while providing attenuation to all other frequencies. While using selectivity, we come across certain terms. One of those terms is skirt selectivity. Here it is defined and described. Skirt selectivity is defined as ratio of 30 dB bandwidth to 3 dB bandwidth for a tuned amplifier. Ratio of 30 dB bandwidth to 3 dB bandwidth. What is it? Usually, response curve appears like this. 3 dB points exist somewhere here. This is the lower 3 dB, upper 3 dB. The distance between them represents a certain frequency range. This frequency range is called 3 dB bandwidth because these are 3 dB points. This distance is 3 dB bandwidth. Like 3 dB points, one can locate 30 dB points also. They may be somewhere here. One 30 dB point, lower 30 dB point, somewhere here you can find upper 30 dB point. The distance between them is 30 dB bandwidth. Skirt selectivity is a ratio of 30 dB bandwidth to 3 dB bandwidth. The range of frequencies between 3 dB points over the response curve is 3 dB bandwidth, and it is usually less than 5% of tuned frequency. Tuned frequency means frequency where impedance is maximum or gain is maximum. 30 dB bandwidth is frequency range between 30 dB points over the response curve. For an ideal amplifier, skirt selectivity is 1. What is ideal amplifier? This is practical amplifier, of course, bell curve. Ideal amplifier is one for which the response curve is like that. It is like a pulse. rectangular pulse. Gain is uniform, independent of frequency. This is lower cutoff frequency, this is a higher cutoff frequency. Lower cutoff frequency can be 0, upper cutoff frequency can be infinity. Ideal case. But in practice, it never happens. So for an ideal amplifier, skirt selectivity is 1, but for practical amplifiers, its value is 3 or even less. Another parameter used while describing the performance of tuned amplifiers is the shape factor. What is it? It is defined as the ratio of 60 dB bandwidth to 6 dB bandwidth. This is a measure of relative selectivity. For a single tuned amplifier, shape factor is approximately 600:1. In a typical case, 6 dB bandwidth is 20 kHz, while 60 dB bandwidth is 12 MHz. Several parallel tuned amplifier stages may be cascaded to reduce the 60 dB bandwidth. What is the shape factor? It is ratio of 60 dB bandwidth to 6 dB bandwidth. What does it mean? In case of practical amplifiers, this is the gain characteristic. 6 dB, see 3 dB points may be somewhere here. 6 dB points may be somewhere here. 6. This is lower, this is upper. The distance is 6 dB bandwidth. 60 dB points may be somewhere here. The distance between them is 60 dB bandwidth. The ratio is shape factor. Another important parameter pertaining to tuned amplifiers is tenability. What is tenability? The ability to stay over a band of frequency for long periods of time. Ability to stay there where it is required to stay. That capability is called tenability. Here it is explained. Another basic requirement of an RF amplifier is its tenability. Thus, it should be possible to time the amplifier over a considerable range of frequencies as desired. Tenability is an important parameter for tuned amplifiers. The reason is these are RF amplifiers, radio frequency amplifiers, so they are working at high frequencies. At high frequencies, drift is a serious problem. If we tune the amplifier to work over a particular band of frequencies, usually the amplifier remains there for some time and then it slowly starts drifting away. This drift is a serious problem and it has to be arrested by taking appropriate remedial measures. So tenability means ability, capability for the amplifier to remain over desired frequency band without drift. Another parameter we encounter frequently in the study of tuned amplifiers is quality factor. Its symbol is Q. Q is a symbol for quality factor. Definition is 2 pi multiplied by maximum energy stored, energy dissipated per cycle. To understand the definition, even though it is quite general, consider an inductor coil, a coil like this. You know well, coils store energy. So maximum energy stored in the coil, energy dissipated per cycle. Notice this coil is made with a conductor. Conductor is not perfect conductor, so it has certain amount of resistance. This resistance causes certain losses. I square R losses, copper losses. Energy dissipated per cycle. That amount of energy gets dissipated per cycle as losses. So quality factor of this coil is 2 pi maximum energy stored by maximum energy dissipated per cycle. This can be shown equal to omega maximum energy stored by power dissipated. What is power? Energy per second is power. It can be shown Q is also equal to resonant frequency to bandwidth ratio. We have seen for LC circuit, response curve is a bell curve. Maximum gain at one frequency, resonant frequency, and gain falls, impedance falls as you move away from the resonant frequency. You can locate 3 dB points on either side. The distance between them is bandwidth. So resonant frequency by bandwidth, it is equal to quality factor. Now, while giving the definition in the explanation, we considered an inductor. With respect to that inductor coil, definition is given some explanation. Now, we consider here coil and a capacitor, inductor and capacitor, and when the definition which we considered earlier is applied, what do we get? For Q, what is the expression for Q? Q is omega L by R for a coil. This expression we got by applying the definition given in the previous slide. What is omega, what is L, what is R? Omega L is frequency, L is, let us suppose here is a coil. Inductance is L. As already mentioned, this inductor is associated with certain resistance. Inductors, they are not wound with perfect conductors. Practical inductor is wound with a practical conductor. Practical conductors are always associated with certain resistance. So this fellow inductor is associated with certain resistance. So the equivalent circuit of this inductor then is pure inductance in series with resistance. This is L, this is R. If we denote R in series with L, Q is omega L by R. The resistance of the inductor, it can also be denoted in parallel with the inductor like this. Inductor resistance. In such case, Q becomes R by omega L. Quality factor can also be defined for a capacitor. Ideal capacitor is one which provides only capacitance, but in practice, it is not possible to have an ideal capacitor. Ideal capacitor is one which gives only capacitance, no inductance, no capacitance, no resistance. Usually, practical capacitors are associated with resistors too. This resistance can be denoted in series with the capacitor, or it can be denoted in parallel with the capacitance. When it is denoted in series, then Q is 1 by omega CR. When resistance is denoted, it is placed in parallel with capacitor, then Q is omega CR. Before going further, the point that is required to be understood as far as the discussion in this slide concerned is coil, condenser. They are associated with a certain resistance. This resistance has to be taken into account. It can be taken into account either by placing a resistor in series or in parallel. If the resistor is placed in series, then expressions given in the first half of the slide, they hold good. If the resistance is placed parallel to the capacitor or inductor, then second half of the relations, they hold good. Classification is there, not one, several classifications are there as far as tuned amplifiers are concerned. One classification is based on coupling. Capacitive coupled amplifiers, inductive or transformer coupled amplifiers. Based on signal amplitude, They can be divided into small signal, large signal amplifiers. In general, if the amplitude of the signal is less than 2.6 millivolts, what is this 2.6? VT, volt equivalent of temperature. It is 26 millivolts. 2.6 is VT by 10. Notice actually amplitude should be much less than, not ordinary less, much less than 2.6 millivolts. Then it is small signal amplifier, otherwise large signal. Based on tuning, single tuned amplifier, double tuned amplifier. Single tuned amplifier means only one tuned circuit exists in the amplifier. Double tuned means two tuned circuits exist in the amplifier. Two tuned circuits. Single tuned circuits. One. Based on tuning, synchronously tuned amplifier. In this type of amplifiers, all the tuned circuits are tuned to one and same frequency. Stagger tuned means these amplifiers employ an RF transformer and its primary and secondary circuits are tuned to slightly different frequencies, one staggered from the other. Staggering is mainly to achieve wider pass band or larger bandwidth. Based on bandwidth also one can classify tuned amplifiers. Narrow band tuned amplifiers, for them pass band is less than 1% of FC. Tuned frequency. Broadband tuned amplifier, pass band is more than few percent of FC. FC stands for central frequency. C stands for center. Here is shown a table where synchronously tuned amplifiers are compared with stagger tuned amplifiers. All the circuits are tuned to one and same frequency, that is center frequency in case of synchronously tuned amplifier, whereas each circuit is tuned to a frequency which is slightly different from the center frequency. This is stagger tuned amplifier. Bandwidth of overall system becomes narrower and gets reduced by a factor of square root of 2 power 1 by n minus 1. The bandwidth of overall system becomes broader. Gain is large when compared to stagger tuned amplifier. Gain is small when compared to synchronously tuned amplifiers. See, basic point is this. People go for synchronously tuned amplifiers when the need is more gain, and people choose stagger tuning when the requirement is more bandwidth. With this, we come to the end of the session. Here, tuned amplifiers are introduced. Selectivity, an important performance index of tuned amplifiers. It has been described: skirt selectivity, shape factor, tenability, quality factor. These are all important parameters we encounter while discussing tuned amplifiers. All these things are introduced and described. Hope this session is useful. We meet again in next session, that is on tuned amplifiers part 2 soon.